Hi friends, it is Amit Avasthi from India. I am going to introduce modular arithmetic, mathematics of remainders. So we are starting from very basic concept that if we are given 10 coins and we have to distribute these 10 coins among 5 students, what happens? Each and every student is getting 2 coins. Exactly 2 coins are there. Each students are having at this moment. Now what happens if we distribute 11 coins among 5 students? Simply again each and every student is having 2 coins. One more coin is there, extra coin, that is remainder. Now think about 11 coins. What happens when we distribute 11 coins among 3 students? So every student is getting 3 coins. We are distributing these 11 among 3 students, so each and every student getting 3 coins. So 9 coins are there distributed. Now remaining coins are 2, so this 2 is remainder. So we can say division is possible in integers if a divided by b and remainder is 0. In this situation we say that b divides a, and we denote by this symbol and read as b is divisor of a. This symbol is read as divisor of a. On the other hand, if division is not possible means if we are dividing things and we are getting some remainder. In such case, we can write this equation where we are dividing a quantities among v people. So each and every person is having q quantities at this moment and r are remaining quantities. So this q, this part is called quotient, and this r, this part is remainder. So in previous example we have already seen that when 10 is divided by 5, 2 into 5 plus 1, this 0 is remainder, and for 11 it was 11 divided by 5, 2 into 5 plus 1, 1 was remainder. Again this was 3. 11 is divided by 3, so in this case 3 times 3, 9 plus 2, 11, and this 2 is remainder. Now in future a mod n means remainder. We denote remainder by symbol a mod n when we divide a by n. Now in some programming languages, instead of writing mod, we use the symbol percentage. This is same mod. In Python there are 2 special operators, slash and percentage symbol. So what happens when we type a / b, it returns always quotient part, and a % b, it always returns remainder part. We can check in Python that 118, when this is / distributed among 13, we will get quotient part, and it is 9. Now for this percentage symbol we can see 13, it gives remainder part, and that is 1. We can check it. 118 is 9 times of 13 plus 1 is remainder. So this symbol is used for remainder. In modular mathematics our interest is remainders. So we say modular mathematics, otherwise we can say remainder mathematics. So a mod n is simply means remainder when we divide a by n. A mod n is read as a modulo n. In Python a mod n is written as a % n. In more detail what modulo returns we can look into these tables. These are the integers, all numbers, -8, -7, -6, -5 and up to 8, 9, 10. So if we are taking at mod 3, what happens? If we take mod of 0, it is always 0. If we take mod of 1, it is less than 3, so it is again 1. If we take mod of 2, so 2 is again less than 3, it returns 3. It cannot be distributed among 3. So now what happens when we goes to 3? So 3 is totally divided by 3. In that case, remainder is 0. Again, what happens with 4? If we divide 4 by 3, we get 1 as remainder. And we divide 5 by 3, we get remainder 2. So what happens? 0, 1, 2. Again it is repeating 0, 1, 2, 0, 1, 2. So repetition of this part is again and again is there. So we can extend this similar structure here for negative numbers. So what happens? If we take mod of -3, remainder of -3 in case of 3, simply it returns 0. What about -8? It returns 1. We can check from Python. Suppose it is given -8 and you have to find remainder. It is 8 and you have to find remainder with 3. It returns 1. So it is nice. We can see from this table and it follows its rule. Now for second table, when we take mod 4, what happens? When we divide 0 by 4, 0 is remaining. We divide 1 by 4, again 1 is remaining there, 1 is remainder. Now 2 divided by 4, 2 is remainder, 3 divided by 4, 3 is remainder. Now when we divide 4 by 4, we get remainder 0. 5, remainder 1. For 6, there is remainder 2. We distribute 7 quantities among 4 people, we get remainder is 3. In this way, here we see that this part is repeated again and again. Now 4 numbers are repeated: 0, 1, 2, 3. One thing more, if we talk about only remainder 1, so what happens? Corresponding to remainder 1, there is -7, and another remainder 1, there is -3, another remainder 1, this is 1, another remainder 1, this is 5. For next one, it is 9. So collection of all these numbers, -7, -3, 1, 5, 7, this is called residue class, and we simply say this is residue class 1. Residue class 1 means collection of 7, -7, -3, 1 and 5 and 9. In similar way, we can make another set for 2. We can make another set for 2. It is -6 for 2. It is -2 for this 2. It is 2 for next 2. It is 6. In this way, collection of -6, -2, 2, 6. This represent residue class with respect to 2. So residue class are represented. So remainder is 0. With these numbers, mod 3 returns 0. With these numbers, mod returns 1, and these classes are called residue class. Now, modular arithmetic. Before proceeding further, we should have some reason that why we are studying modular arithmetic. So here are some applications are: how do we efficiently store people's record? There are, this is 10 to the power 10. if we have to arrange 10 to the power 10 numbers, social security numbers, how can we arrange these numbers? Solution is hidden in modular arithmetic. How do we generate a random number? Again, solution is in modular arithmetic. ISBN number, this number is given to books, and there is some pattern in that, and at last digit we are having a check number, and which ensures that all other numbers are correct. So again, use of mathematics here, modular mathematics. You can search Google or Wikipedia for this purpose. And a huge use of modular arithmetics in cryptography. We are dealing with secure communication. Now, modular arithmetic. First thing is modular equivalence. The idea is that we want to say that A and B are equivalent. When we can say that A and B are equivalent? Yes, we go back to the classes, residue classes. When remainder was 1, minus 7. When remainder was 3, minus 3. When remainder was 1, it was 1. When remainder was 1, it was 5. So these minus 7, minus 3 and 1 and 5, these all returns same remainder. So we say these are equivalent. These numbers are equivalents. So when we divide A by M, we get remainder R. When we divide B by same number M, and we get remainder R, so remainder in both cases same, we say that these two numbers are equivalent, and we write this A equivalent to B modulo N. Condition is N is divisor of these both quantity. We can check if you subtract B, A minus B, simply M common, S minus T, it becomes A minus B is equal to M common, and it is S minus T, and this part becomes 0. So we can say that M divides A minus B. So A is said to be equivalent to B modulo N if and only if N divides this difference A minus B. Rather than say integers A and B are equivalent, we say congruent modulo N. A congruent modulo A congruent B modulo N. Very well known clock math. Just we are taking here one example. Suppose question is, it is 7 o'clock. We are not dealing with it is AM or PM, whatever. It is 7 o'clock, and hence our hand is at 7 in hand watch. Where will be the our hand after 7 hours? Obviously, currently there is 7, so we can add again 7, 7, 7, 14. But what happens? It has only 12 hours. 0, 1, 2, 3, 4 up to 12. And for 13 it will go to 1, and for 14 it will go to 2. Intuitively we can say that 14 is equivalent to 2. And in terms of mathematics, 7 plus 7 modulo 12. It is 14 modulo 12, and 14 and 12, these are congruent. 14 and 2 are congruent. You can check 14 minus 2, this is divided by 14 minus 2 is divisible by 12. So therefore 14 and 2 are congruent. So 14 is equal to 2 mod M. 2 is, and we can check from Python also, 14 mod 12 returns 2. So 2 is remainder of 7 plus 7 modulo 12 when 14 is divided by 12. So this is 2, same as whatever intuitively guessed here. So 14 mod 12 is equal to 2 mod 12 means 14 o'clock and 2 o'clock. These look at the same on 12 hour clock. They are congruent. 14 is congruent to 12. Modular arithmetic. We have already discussed residue classes. So what happens with these numbers, if you take modulo 3, we get remainder 0. With these numbers, remainder 1. With these numbers, remainder 2. There are only 3 possibilities with modulo 3 because there is no remainder 4. Now when we are doing these operations, plus, minus, multiplication over modulo n, we can replace a number by another number in the same residue class. Like we are adding 4 and 7. So 4 plus 7, it is simply 11. If we are dealing with modulo class 3, what happens? 2. Sorry. Modulo addition plus n. A plus b mod n. This is same a mod n plus b mod n. So we can add numbers before and then take mod, or we can take mod first and then we add these numbers. What if this number comes greater than n? Now we can take again mod of this. So example is 2, 7 modulo 5. This symbol is modulo n addition. So 2 plus 5, 7, it means modulo 5. 7 plus 2, this is 9. 9 modulo 5, it produces 4. Again for 22 we can check 22 plus 72. Simply you can check, it is 2 to 4, 7 to 9, 94, and if you take mod 5, it gives 4. Second method, by this part we can do this thing: 22 mod 5, 72 mod 5. 22 mod 5 returns 2, and 72 mod 5 returns again 2. So we can add these numbers. 2 plus 2, this returns 4 mod 5. This is 4. So same thing we can do any method, first method or second method. This is arithmetic addition. Similar result is for modulo addition, modulo multiplication. Sorry, it is multiplication. Two into 7, this is 14, and we are taking mod at 4, it is 4. Similar 22, 72 modulo 5, we can check from Python, same results. 22, 72 mod. For mod we use percentage symbol, and mod 5, this returns 4. And same thing we can do here: 22 percent 5 into 72 percent 5. So this is again 4. In both way we can do this computation. So second method becomes too good when we are dealing with long numbers. Like if we have to multiply this, so what happens? First we have to multiply these two numbers and we will get a huge number, and then we take mod, it will return 3. So other method is we simply can take mod of first part and 3, 4, 5, 6 mod of second part, and we get same result. So sometimes second method becomes too easy and too fast. Modulo inverse. So this concept is very important concept, and particularly for cryptography it is the base of cryptography, we can say, for many protocols. What is inverse? Actually, if B are taking product of A with B and we are getting 1 modulo n, then we say this B is inverse of A modulo n. A and B are inverse of each other. So we can see A is inverse of B and B is inverse of A. Normally, if we discuss for A, simply B is inverse of A, and we write this thing as B is equal to A inverse mod n. Important factor is this: inverse of A is possible only if A is relatively prime to n. This, what is relatively prime? Relatively prime means if we are taking two numbers and nothing is common between these two numbers. If we are bounded to have integer calculation only. Look here, 3 7, nothing common, 4 7, 5 6. So therefore these combinations are relatively prime. And what about 2 4? In 2 4 we can take 2 common, because this is 2 into 1, this is 2 into 2. So in this case 2 4 combination is not relatively prime. So for inverse, if we are computing inverse of A with modulo n, in that case A must be relatively prime with n. If it is not, we cannot find inverse of A. Inverse is not too easy, so here I am providing an algorithm. By this we can compute inverse. But here, to understand the concept of inverse, I am taking very simple example. 3 inverse mod 7. Actually we have to find the inverse of 3. 3 inverse may be written as 1 by 3. 1 by 3 mod 7. Now add this 7 in this 1. So it becomes 8 by 3. So this is not an integer. Again repeat this process. Now it is 8 plus 7. This is 15 by 3. Now it is integer. We can divide 15 by 3 and we get 5. So 5 is inverse of 3. We can check 3 into 5. This is 15 mod 7, and 15 mod 7 is equivalent to 1. Some important results are: if A is congruent to B and C is congruent to B, then A plus C is always, addition of these two always equivalent to addition of these two. Difference A minus C is always equivalent to B minus D. Product A cross C is always equivalent to B cross D. So we can use these results. Important fact is here, although it calculation seems similar to integers, what important difference is here, that addition of two numbers or multiplication of two numbers may be 0. But in integers, for positive integers especially, it is not possible that you add two numbers and you will get addition of that number is 0. If you are adding 2 and 2, that gives always 4. But if we are adding 2 with 2 modulo 4, we get 2 plus 2 is equal to 4, and that is 0. So addition of two numbers may be 0 here, which is not true for integers. Summation, in summation this possibility is there for one negative integer and another positive integer. But for product there is no possibility that we are multiplying two numbers and we are getting 0. We are having a criteria that if product of two numbers is 0, then at least one number must be equal to 0. So this is not true in this case. We are having two numbers 2 and 2, and we are taking modulo of this, we are getting 4. So product of A into B, these numbers may be A, B, different numbers. There are other possibilities also there. So for examples, it may be 1 into 4. It is 1, it is 4, again 4. So in this case, product of AB is equal to 0. Neither A0 nor B0. So this is important fact. we should have in mind. Now, thanks.